Hello guys, welcome back to In 5 Minutes. In this presentation we are going to design a counter which is asked in a December 2015 exam, and the question is like, design a synchronous counter to count the sequence 0, 1, 2, 3, 4, 5 and 5. Again it is written into 0. So depending on this, writing solution part first. First of all, in design you need to have the state diagram. So state diagram. So in the state diagram part, let me design the state diagram. States are written here: 0, 1, 2, 3, 4 and 5. Okay, state number 0 is going to 1 is going to 2, 2 is going to 3, 3 is going to 4, 4 is going to 5 and 5 is going to 0. Okay, so let me identify here. Since it is a closed path, let us say that let 0 be the reset state, according to which we will design the circuit considering 0 as the reset state. Along with this, what we need to do, since the maximum number of state is 6 or 5 here, the states involved are 6. Okay, 0 to 5, so n is equal to 6, but the formula is like n should be less than or equal to 2 raised to power m, and n here is 6, so 6 should be less than or equal to 2 raised to m. So therefore value of m will be equal to 3. That is nothing but, therefore 3 flip-flops will be required. Okay, now for these 3 flip-flops required, let us draw the truth table. So for truth table for these 3 flip-flops will be like, here let us design the truth table having present state, next state. So we have here present states. Okay, according to present state, next state, and inputs to flip-flop from excitation table. Okay, now this flip-flop inputs presented, let this 3 flip-flops will be having output QC, QB, QA. Next state will be QC plus 1, QB plus 1 and Q of A plus 1. Whereas input to flip-flops will be D. Let us say we are using the D flip-flop, so it will be DC, DB and DA. Okay, so delay type of flip-flop we are going to use to design this synchronous counter. In synchronous, the clock pulse is simultaneously given to all the 3 flip-flops. So present state, if you consider, there will be 8 combinations starting from decimal equivalent state number 0 to 7. So these are the states, out of which 0 to 5 states we are using, but 6 and 7 state we are not using. So instead, for the next state of 6 and 7 we will put a don't care. Okay, but before putting up the don't care, let us design for the states which are involved here actually. So starting from the reset state, 0 goes to 1, so I'll write here 0 0 1, 1 goes to 2, that is 0 1 0, 2 goes to 3, 0 1 1, 3 goes to 4, 1 0 0, 4 goes to 5, that is 1 0 1, 5 goes to 0, that will be 0 0 0. So instead of putting a don't care condition here, why we are not putting a don't care condition? Because the counter may enter into the lockout conditions. To avoid that, let us design a lockout free case. So state number 6 and state number 7 which are not used. Okay, so for state number 6 and state number 7, put the states into the reset state. So what will happen if the counter may try to enter into state number 6 or state number 7 which are not used? The counter will be fed back into the reset position and it will start counting from the initial state, that is nothing but the reset state, according to which we are going to design the circuit. So instead of putting don't care, we have designed a lockout free. So this is the bushing technique. So I am writing here bushing technique. Or one more important point I'll mention here, it is a lockout free state diagram. Okay, so what I will do here, I will put state number 6 to 0 as well as state number 7 to 0. Okay, now we all know that the excitation table for D flip-flop is a delayed, it shows the output as a delayed input. So whatever the next state logic, that will be copied as it is. That's why I am considering the D flip-flop. See, we have to make sure that whenever you are asked to design a synchronous counter but the flip-flop should be used, as it is not mentioned in the question paper, you always need to solve it by D flip-flop, because it is very easy to solve it with D flip-flop. So next state column is copied as it is here. So I'll copy the next state column as it is. That's why I'm using a D flip-flop here. Now depending upon this D flip-flop, we need to solve the K maps for DC, DB and DA.